Welcome, friends. Let's work through a problem that's really similar to the one in our recent problem set, number 4. Question number 2. That one had a lot of moving parts, and there was some confusion about different aspects of it. So let's go through a problem that's very similar to it. All right. So here it is. You combine 35.0 milliliters of 0.115 molar lithium sulfide with 45.0 milliliters of 0.285 molar copper-1 chloride and a solid forms. So your first job is to write molecular, full ionic, and net ionic reactions. So pause the video if you need to, so you can work through it on your own. But obviously we're going to be reviewing some skills from chapter 3 here as well, where we have to write the formulas from the name and write and balance a reaction. But we're going to combine that with the new skill of using our solubility rules as well to predict which of our products forms the solid, so that we can then go through the process of working through molecular, full ionic, and net ionic. Okay, so we'll start with lithium sulfide. It's an ionic compound made of lithium and just sulfur. That's not one of our polyatomic ions. Lithium has a +1 charge, and sulfur tends to get a -2 charge. So we'll need 2 lithiums for every 1 sulfur. Okay, and we're told that this is a solution, so we know it's aqueous. Okay, and it's going to react with copper-1 chloride. So remember, the Roman numbers tell us the charge on the copper because we can't figure it out from the periodic table. So that means it's copper with a 1+ charge. Chlorine typically gets a -1 charge, so we just need 1 of each. And again, we know it's aqueous because we were told it's in a solution to begin with. All right, so what forms here is going to be a swapping of the partners. The positive ions are going to pick up the negative ions on the other compound, and the negative ions are going to pick up the positive ions on the other compound as well. So we're going to put lithium with chlorine, and again, we're not going to worry about this 2 right now. We're just going to focus on the ions and how they are, and we'll deal with that balancing in a minute. Right, so lithium's a +1, chlorine's a -1. So we'll just need 1 of each. And we'll leave a space. We'll decide if that's aqueous or not in a minute. And then copper-1, the 1+ charge. Sulfur still has a -2 charge. So we'll need 2 of those coppers. Right? And again, note I'm not worried yet about balancing. First, I'll deal with which of these 2 compounds is a solid. We know one of them is. That was a hint in our problem there. So we'll look at our solubility rules and realize that both lithium and chlorine tend to be insoluble compounds with a few exceptions. So this is actually going to be our aqueous one. Our lithium chloride will be aqueous. By default, that makes this other one our solid, but we can check the solubility rules, and that is that sulfide compounds are insoluble. That means they don't dissolve. That means they'll be the solids, with, again, a few exceptions. None of which are copper-1. So we'll put an S down there at the end for this one. And now we need to balance when all is said and done. And hopefully we've written our formulas correctly. This should balance with just a 2 or a 3 or a small whole number here or there. All right, so there's our molecular equation. The full ionic is to show how these compounds really exist when they're dissolved. And if ionic compounds, they will break up into the ions that form them, right? Not into the elements that form them, but into the ions that form them. So we need to make sure that we're writing ions here. That was something that was missing in the problem set. A lot of folks forgot their charges, but you did handle the numbers and the balancing pretty well. So when lithium sulfide goes into water, it'll break up into 2 lithium ions that are aqueous and 1 sulfur ion that's aqueous. We'll do the same thing for the copper-1 chloride. It will break up into the ions that form it. And remember, this 2 out front means we have to double the amount of everything that's in there. That means we'll have 2 copper-1 ions in the water, aqueous, plus 2 chlorine ions, aqueous in the water. Right, we'll put our arrow there. Lithium chloride is aqueous, so it will break up into 2 lithium ions plus 2 chlorine ions. Okay, and our solid stays together. All right, so now we've accounted for the way these ions are actually behaving in the solution. Right? Some of them are free floating and some of them are bound up in a solid. These ones over here. So the net process is to cross off the things that are identical on both sides in terms of numbers and in terms of phases. Are they aqueous? Are they solid? And their charges. So we'll see, grab my other pen. We have 2 lithium ions on both sides and we have 2 chlorine ions on both sides. So they won't be part of our net process. Our net process is 2 copper 1 ions, aqueous, plus a sulfide ion, aqueous, makes copper 1 sulfide solid. Oops. All right, so that is the first part of the problem, understanding what's going on with our system. Right? So let's move on to the quantitative part of this. Right? Just like in our problem set, the question is, what is the molarity of each ion present just after the solutions are mixed, but before any reaction happens? Okay? So we need to account for the fact that these compounds are breaking up into smaller pieces just from being in the water. Okay? So I'm going to put the formulas of our compounds over here so we can remember what they are. Okay. And we have 35 milliliters of 0.115 molar lithium sulfide. Okay. When this goes into the water, we're going to get twice as many lithium ions as we had lithium sulfide units. So we will have 0.230 molar lithium ions. And the sulfide, we're just going to get 1 for every 1 unit we started with. So the sulfide ions will be at 0.115 molar. That's our sulfide ion concentration when it's in its own container before we've done anything to it. And we'll do the same thinking over here for the copper 1 chloride. Both of these are 1s, right? We're going to get 1 of each ion for the units of copper 1 chloride we started with. So the copper will be 0.285 molar, copper 1, and the chlorine will be 0.285 molar, chlorine ion. So that's what they are when they're in their own little containers before we do any, we haven't even done any mixing yet. We've just accounted for the fact that they are existing in their own little beakers the way they are. Note that we haven't even looked at our reaction at this point, right? Right now, these poor little ions don't know what's coming. They don't realize there's a reaction happening. So their concentrations are independent of that reaction right now. So let's mix them together. Let's pour them into the same container, right? You can see what's going to happen is our total volume is now going to be 80.0 milliliters, right? And these concentrations are going to be diluted in some form. Let's take a look at that sort of pictorially. Okay. So remember in here, we have no reactions happened yet. We have lithium ions, we have sulfide ions, we have copper 1 ions, we have chloride ions. And the volume is now 80.0 milliliters. Okay. They're all sharing the space now. They haven't done any reactions yet. So we have to account for the fact that those concentrations we had on the previous page they've all been diluted. So we can do a dilution calculation for each of our ions to see what's happened to them just by being combined into this bigger volume. They've got more space to run around in. So for example, our lithium ion, oops, it's a 1+. Got a little carried away there. 1+ ion. It was originally, its M1 was originally 0.230 molar. Its original volume was what it was, right, when we picked it up off the shelf. It was 35.0 milliliters. Our final molarity, when it's all been diluted, that's what we're looking for. And our final volume is this new combined volume that everything is running around in, 80.0 milliliters. So we can set this up like a dilution problem and solve for the missing part. M1 V1 equals M2 V2. And we can leave our volume units in any unit we want as long as it's the same on both sides. And so we'll just leave it in milliliters. Equals, and then M2 is what we're looking for, and V2 is 80.0 milliliters. So our final molarity, or our new molarity, when everything's been diluted, grab our calculator there, 0.230 times 35 divided by 80. And the new molarity for lithium is 0.1. We're going to have 3 significant figures, 101 moles per liter. Okay. So go ahead and pause the video and work through what the molarities are for these other ions that we have here initially. So remember, this is after they've been mixed, but before any reactions happen. So it's kind of like creating a new starting point once they've all gotten into the same container there. So go ahead and pause that and work through that, and I will get some of our values over here for the other ones. Okay, so if you've got everything worked out, we should have that, again, the molarity after dilution for the lithium ion is 0.101 moles per liter. For the sulfide ion, it's been diluted from its original value to 0.0503 moles per liter. And the copper and the chlorine were the same, and they've both been diluted to 0.160 moles per liter. Okay, so we'll keep those values in mind because now we can move forward with this as sort of our, again, like I said, our sort of our new starting point for our ions. All right, so here's the follow-up question, and that is, what mass of solid forms? Let me remind us of what our net process was. We had copper ions reacting with sulfide ions to make copper 1 sulfide solid. We'll get that all balanced there. Okay, and we know that we have 80 milliliters of, right, and we know what the copper concentration is, 80 milliliters of 0.160 moles per liter copper ion. And now, because they're swimming in the same container, we have 80 milliliters of 0.0503 moles per liter sulfide ion. Okay. So we have information about both of our starting materials. We have information about the copper concentration or moles, right, since we know the volume as well. And we have information about the sulfide ion. What should be happening in your heads right now is you should be thinking, this is one of those dreaded limiting reactant problems. Right? That's the little flag that should be waving in the back of your mind. You should be seeing, whenever you see starting information about both of your reactants, you're going to have to solve a limiting reactant problem. And again, for us, we can just go ahead and use the net reaction, since all of our questions were referring to the ions individually and not the compounds that they came from. We can work with the net reaction here and see how that works out for us. Okay, so remember, with the limiting reactant problem, what we're going to do is we're going to solve the problem, solve the what mass of solid forms, what mass of copper 1 sulfide forms for each of our starting materials, and then we will decide which of them forms the least amount of product, the least amount of solid in this case, and that will be our limiting reactant. Okay, so we can start with any one we want. I'll start with copper, since it's right on top there. Right, and we know the milliliters of our copper 1 solution. Right? And in order to use our reaction, we have to get to moles. And in order to get to moles for a solution, we have to be in liters of our copper 1 solution. And then we can use our molarity to get to moles of just our copper 1 that we're interested in. Now that we're in moles, we can use our balanced reaction and those coefficients to change it into moles of copper 1 sulfide. And then lastly, since we wanted mass eventually, we can change from moles to grams of our copper sulfide. Okay. So for this first one, we need to know a prefix, one of those things we're supposed to have memorized. For the second one, we're going to use molarity as a conversion factor. The third one is our mole ratio from our balanced reaction. And then lastly is the molar mass of copper 1 sulfide. Okay. So those are, again, some pieces we've seen before with molar mass and mole ratio, but now we're combining it with using molarity as a conversion factor, along with in this bigger problem of a limiting reactant problem. So let's put those values in and come up with a number, and then we'll do the same thing for the sulfide ion. Again, feel free to pause the video and give yourself a chance to kind of work it out on your own there. All right, so we'll start with 80 milliliters of the copper solution. And there is, for every 1 milliliter, 10 to the minus 3 liters of that solution. Okay. Our molarity was 0.160 moles per liter. So I'll put my liters in the bottom. 1 liter of my copper solution has 0.160 moles of my copper ion. Now my balanced reaction, I have 2 moles of copper ion for every 1 mole of my product that I'm interested in, copper 1 sulfide. And then I need to go to the periodic table and figure out the molar mass of copper 1 sulfide. And it is 159.2 grams of copper 1 sulfide for every mole of copper 1 sulfide. So we'll need to come up with a value for that. That times our molarity divided by the mole ratio times our molar mass. And we get to, again, we have 3 significant figures here. We're limited by both the molarity and our starting value, 1.02 grams of copper 1 sulfide. Okay, and that might be the answer, but we won't know until we check out and see what's going on with the sulfide ion. So it'll be a similar process for the sulfide ion. Let me switch to a different color so we'll be able to tell them apart. So it'll be 80 milliliters of, this time, the sulfide solution. Okay, the prefix is the same. That's the same for all conversions between milliliters and liters. Okay. What's different is the molarity for the sulfide. Okay. It's 0.0503 moles of sulfide ion for every 1 liter of the sulfide solution. Okay. Our mole ratio is also different, right, from our balanced reaction. 1 mole of sulfide for every 1 mole of our copper 1 sulfide. And then the molar mass is the same. 1 mole of copper sulfide, 159.2 grams of copper 1 sulfide. So let's see what this gives us. Times molarity times the mole ratio times the molar mass. And this gives me 0.641 grams of copper 1 sulfide. Okay, so now, because it's a limiting reactant problem, we have to make a decision. We have to decide, well, which amount of product actually forms? What's our limiting reactant here? So for us, we look and we say, this is the smallest amount that can form. So it limits us. We can't form more than that. Once we've formed that amount of product, we're all out of copper. We're all out of the sulfide ion. It's all gone. It's completely used up. So the answer to our question is 0.641 grams of copper 1 sulfide forms, and the sulfide ion is our limiting reactant. Okay, we might need that information in a little bit. Is our limiting reactant. Okay. All right. Let's go on to the next question, which was a little bit more of a challenge. Again, a few folks forgot about the limiting reactant aspect of this problem on our problem set. But let's check out how we would follow through and finish this question all the way to the end. So this was the last bit, which was one of the more challenging problems, again, by design, because it's going to deal with both what's used up and what's left over. That's always a challenge for us. Okay, so let's do the easy ions. Remember, there were 4 ions there at the beginning. Our limiting reactant is all gone, right? Our sulfide ion, which is our limiting reactant, there's my lazy person's abbreviation for it. Sulfide ion was our limiting reactant. So what that means is at the end of the reaction, the concentration or the molarity of the sulfide ion is 0 moles per liter, right? Because it's all used up. That's what a limiting reactant is. It's all used up. That's our definition of a limiting reactant. Okay? It's all been converted into that solid. It's not gone. It's just no longer existing as a free sulfide ion swimming around in our bucket. Some other easy ones to do. We had those spectator ions, the ones that we haven't been paying attention to. So that would be our chlorine ions and our lithium ions. Okay? These two were our spectators. Okay? And what that means is that they are unchanged. They weren't involved in this reaction at all. So we can go back and look at what their concentrations were at the beginning, right? After we diluted, after we mixed them and diluted them. And our chlorine ion concentration at that point was 0.160 moles per liter. And at the end of the reaction, it's still 0.160 moles per liter. It hasn't changed there. It's the spectator. And we do the same for the lithium. It's originally, once we got everything mixed together and diluted, was 0.101 moles per liter. And it is also unchanged. That's just what it means to be a spectator ion. You didn't do anything. You just watched. So your concentration wasn't affected. None of your little ions were used for anything. All right, so that leaves us the more challenging one, right? The copper 1 ion. It had an initial concentration right? There was some there at the beginning. We know that some of it was used up to do this reaction with the sulfide ion, but not all of it. So for copper, we're going to have to first determine the moles at the beginning, how many moles were present at the beginning. Then we'll have to determine, right, calculate using stoichiometry, the moles of copper ion used in reacting with that sulfide ion amount that we had. Okay? So again, this is going to depend on what we actually combine together. Okay? And then we will do a subtraction to find out what's left over. Right? So we have to know where we start and what got used up, and that'll tell us what's left over, and we can then convert that into a molarity. Okay? So how are we going to find how much was used? Well, we'll do a stoichiometry calculation. We know how much sulfide was used, so we can relate that to the amount of copper that was used in terms of moles. And to determine the moles at the beginning, we know the original volume and the original concentration, so we can find moles there. Okay, so let's start with our beginning. Okay, so at the beginning, we had 0.160 moles per liter, and we had 80 milliliters of it, right? Originally, after we combined everything, we had 80 milliliters of that solution. And we can change that into liters. 1 milliliter, 10 to the minus 3 liters. Okay, now we'll use our molarity to get us into moles of copper ion that was there at the beginning. And our concentration was 0.160 moles of copper ion for every liter of the copper solution. All right, so if we do our calculations, we can find that at the beginning, there was 0.0128 moles of copper ion. That was our initial amount, which is not helpful quite just all by itself. We need to do the second part. We need to figure out how many moles got used up reacting with all of the sulfide ion that we started with. Okay. So we're going to start with our sulfide ion, right? And we're going to use our balanced reaction to tell us how many moles of copper would have reacted with all that. So again, we're going to start with what we know about the sulfide ion, and it was in that same 80 milliliters. Okay, we still need to get into liters. 1 milliliter, 10 to the minus 3 liters. Okay. And remember, this is the sulfide ion we're still talking about. So this is the sulfide ion solution. Okay. So we're going to use the concentration of the sulfide ion. Again, before it all reacted, we have 0.0503 moles of sulfide ion per liter of the sulfide solution. Okay. And remember, our goal was to figure out what's going on with the copper. How did the copper combine with it? In what proportion? So we look back at our reaction and we look for what that proportion is. And there were 2 moles of copper ion for every 1 mole of sulfide ion. And this will tell us the moles of copper that were actually combined or changed or used up in our reaction. So let's get our calculators out again and find out what that is. Oops, 0.08 3 times 2. We get 0.00805 moles of copper ion. All right. So now we know the moles of copper we had at the beginning. we know the moles of copper that have been consumed. We have to do a subtraction. So the leftover amount of copper is our beginning amount, 0.0128 moles of copper, minus the amount that was used, 0.00805 moles. And when we do that subtraction to the right number of significant figures, remember we're doing adding and subtracting, so it's decimal places, not total number of significant figures. 0.00805. And we get to 4 decimal places, 0.0047 moles of copper ion. That's what is sitting there, left over, unused, still there at the end, which is exactly what our question was about. It asked for the molarity at the end of the reaction when it was all done. That's not a molarity, that's moles. So we do need to divide it by the number of liters. Move this over so we can see it. So the molarity of our copper is the moles, 0.0047 moles, over the liters. Remember, it's in the 80 milliliters. So maybe by now you can do this in your head, 0.0800 liters. Okay, don't lose those significant figures. 0.0047 divided by 0.08. And our molarity of our copper at the end of the day is 0.059 big M moles per liter. All right, so now we have answered all the questions in this rather lengthy problem. But that gives you a sense of the sorts of, really all of the sorts of things we're kind of putting together here between chapters 3 and 4 as we're working through this. So thank you for joining me for this question that was sort of similar to problem set 4, question 2. Do review that in your answers, the answer key to that problem. And thank you for joining me, and we'll see you soon.